In this video, I'm going to discuss about how to analyze a doubly reinforced section of a beam section. This is a beam section and how to analyze it. Here, my main task is to find the required compression reinforcement and how to find the moment of resistance of this beam section. Okay, let's start. First, I will draw that section again. This is the section we have to analyze. We don't know the compression zone reinforcement, and here in tensile zone there are two T25 bars and the effective depth is 300 millimeter there, and the depth for the compression bars is 50 millimeters, and here the 50 millimeter for the bottom, so the total depth is 350 millimeters, and the width is 150 millimeters. Okay, here as you know there are two zones in the a beam as compression zone and tensile zone. Compression zone is located over the neutral axis, and this is the neutral axis. According to BS 8110, the maximum depth for the neutral axis for the yield of the reinforcement is x. We have to maintain x over d must be below or equal to 0.5. We can check it in the clause 3.4.4.4 clause. You can check it. Okay, let's assume that the neutral axis, the depth of the neutral axis is equal to 150, and we have to find the area of the compression zone reinforcement. As here d dash over x, here d dash means the depth for the effective depth for the compression zone reinforcement. It is 50 over 150 is 0.33. As it is lesser than 0.43, that compression reinforcement is also at yield stage. These bars also at yield stage. So as the forces inside the tensile bar or the forces inside the beam is balanced or at the equilibrium stage, we can take that tensile forces are equal to the compression forces. Here tensile forces are carried by the tension reinforcement while compression is carried by two components. What are they? They are compression reinforcement and concrete. Here concrete means the concrete in the compression zone, not by the whole concrete, it's by the concrete inside the compression zone. Okay, as tensile forces are equal to compression forces, we can take that the the tensile force carried by the tensile force is equal to 0.87 into Fy into As. Here, these values are from the BS 8110. These are according to BS 8110. We can see these equations there. And here, compression zone still also give this much of compression for the equilibrium. Here the area is the compression zone reinforcement area, and by the concrete, here this 0.9, we can see it in BS 8110, and because of that we use 0.9 there. Okay, let's substitute the values we know. 0.87, Fy is equal to 460, and As, here As means the area of steel inside the tensile zone. It's equal to 2 into 5. R is equal to 12.5. It means 25 over 12. It's near 981 square millimeters, equal to the 0.87 into 460 into AX bar we don't know it, we have to find it, and the values of concrete, we take it as the strength of the concrete, take it as 25 over 0.9 over 150. 150 means the width of the section, and the depth of the neutral axis also equal to 150. I'll write it again. As that one is not much clear. 0.87 into 460 into 981 equals 0.87 into 460 into AS dash, as we don't know it, we put it as S dash, plus 0.45 into 25, this is the strength of the concrete, into 0.9 into 150 into 150. Here this 25 is the strength of the concrete. That is the strength of the concrete. Okay. Then we can find the value for AS. AS dash. We can take it as 412 square millimeters. It means we have to understand that we need 412 square millimeter of compression reinforcement to balance the beam section. Okay, it means we provide compression steel with 412 square millimeters. Okay, but we cannot add any amount of reinforcement into a beam section according to BS 8110. We can refer table 3.2 0.27. This will give how much of minimum reinforcement we have to supply for minimum reinforcement. It is 0.2%. This is the minimum compression reinforcement we have to supply. Okay, let's check that how much of reinforcement percentage of reinforcement we have supplied. Here this 0.2% is from the concrete section area. It means AS dash over concrete area must be greater than or equal to the greater than or equal to the 0.2%. As our general practice, we take it as 100 AS dash over AC. Let's check what's the value for it. AS dash is 412. AC is equal to the this is the total concrete area, not the compression zone. This is the total or the section area, that is equal to 350 into 150. Okay, that is equal, the value is equal to 0.86, that is greater than 0.2. So that is okay. Can it means satisfied. The compression zone reinforcement is enough. Okay, let's moment of resistance of this beam. How we can find it? For that, first we have to find the depth of the lever arm. Lever arm, here we lever arm is equal to, that is Z, lever arm is Z, is equal to D minus 0.45 into D over 2. Here D is equal to 300 into 0.545 into 300 over 2, that is equal to 132.5 millimeters. It means the lever arm means lever arm means the distance between the tensile force and the compression force. It means it's like this. In a beam, the moment of resistance is equal to the couple that create by using this compression force and the tensile force. It means we can find it by using T into Z or C into Z, that is equal to the moment of resistance. The depth of the lever arm is equal to 232.5, and the tensile force, we know it is equal to 0.87 FYAS. Here FY is 460 and AS is 981. Okay, here we are going to find the moment of resistance. As we know that the lever arm of the concrete section to this tensile bar is equal to 2 232, but we have to find the depth or the lever arm for the reinforcement here, that is equal to 250, as this one is 50 and the depth for the reinforcement bar from the top is 300, and by this calculation we can take that the depth between or the distance between top and bottom reinforcement is equal to 250. Then how we can find it? How we can find the moment of resistance here? Here here this is a special thing, or these values are taken with my experience. We have to take the moment of resistance by compression steel and moment of resistance between concrete and reinforcement. How we can find it? Okay, I will tell how we can find it. For the compression steel, it is 0.87 Fy S dash into 250. What's that 250? 250 means the distance between two tensile bars. Sorry, two bars. It means top and bottom steel bars. 250. And the concrete section, it is 0.45 FCU. We take it as 25 AC. It means it is equal to 0.9 into neutral axis into the width into, this is the most important one, this is 232.5. That's the value we taken here by using this equation o d minus 0.45 into d over 2. This is for concrete section. This is for concrete section. Okay. Now we know how these values are came here. This 250 is distance between top and bottom steel bars, and this is between concrete section and reinforcement, tensile reinforcement. Okay, let's find the values here. 0.87 into 460 into 412 into 250 plus 0.45 into FCO is 25 into AC. AC is here equal to the compression zone area of the compression zone, that is 0.9 into 150 into 150. This 150 is depth of the neural axis and this 150 is width. This is width and this one is x. X means the neural axis, depth of the neural axis. The final answer for the moment of resistance is equal to the 94187,006 Newton millimeter. We can simplify further it as 92.94.2 kilo Newton meters. This is the moment of resistance of this beam. By using a calculator, you can simplify these values and you can take this one. This is the moment of resistance. Moment of resistance of the beam. It means this is the bending moment with that beam can resist. Okay, thank you for your time on my videos, and I hope to take more and more videos, more and more valuable videos for civil engineers in the future videos. Thank you. See you again.